Up next is Dr. Daniel Gruner, CTO of the SciNet High Performance Computing Consortium at the University of Toronto, which runs the fastest academic computer systems in Canada. Dr. Gruner has more than 30 years experience in computational science and scientific computing, working with a variety of programming languages, parallel computing, scientific modeling, software architecture. He earned a bachelor's degree in chemistry and physics from the Hebrew University of Jerusalem and a doctorate in chemical physics from the University of Toronto. Today, Dr. Gruner will present Niagara, Canada's fastest supercomputer. Thank you for joining us today, Dr. Gruner. You may begin.
Thank you for your kind invitation. I'm very happy to be here. And I'm following on the steps of some very interesting presentations yesterday and Jeremy's presentation on I/O today. This is, I/O is the Achilles heel of what we do, and oftentimes it's been an afterthought. So it's really important that we build balanced systems as much as we can. There's also the minor detail of money, right? But anyway, so I'm going to tell you a little bit about who we are and about the system that we built. As you can see, SciNet is one of the high-performance computing installations in Canada. There's 5 of us. We cater to all of academia in Canada, basically. The main impetus for the SciNet design was to build a system that was suitable for large parallel computations. Most of the other systems are general purpose, and they're not necessarily as well balanced for being able to run, say, on the full system that we have. So I'm going to tell you a bit about how we went about building it and some of the features within it. The original spec, so the system that came online at the beginning of 2018, is as I'm showing you here. So it's 60,000 cores of x86, 1,500 nodes, each with 40 cores, connected with InfiniBand. The catch here with the InfiniBand is that we're using a Dragonfly topology, which is, it was the first available, or the first installation of a Dragonfly, at least in the open world. I don't know what happens, behind the 3-letter acronyms and the like. So the idea for the Dragonfly is, again, performance and economics. Initially, we had 10 petabytes of spinning disk. Our file systems are all GPFS, or spectrum scale, if you like to call it now. And in addition to the spinning disk, this is all provided by Lenovo, by the way, we also installed this. We also installed a what we wanted to call initially a burst buffer, but it's basically another tier of storage built out of NVMe, and on top of it is running the Accelero software. So it really is 512 terabytes of NVMe disk, but we're running it in a RAID 10 configuration for reliability, so we have 256 terabytes. And it can do very high IOPS. I don't know the numbers, but it's very high compared to what spinning disk can do. In terms of bandwidth, it was higher than the original 10 petabytes of spinning disk. But the main issue with it is the fact that you can use it as temporary storage for I/O-intensive jobs. As we all know, I/O is really bad. The less I/O you do, the better. But hey, you got to save your data somehow, and you have to read it back in. Initially, when it came out, we were number 53 in the top 500, whatever that means. I mean, it's not an extremely useful measure, but it still means that we were the fastest system in the country. So that was 2.5 years ago. The 685 kilowatt power consumption is to illustrate that it's much, much more energy efficient than the system we used to have. We used to have 30,000 cores of x86. that came online in 2009, we ended up with a new system that was about 10 times as powerful. It used 40% or 50% of the power, and used a lot less space as well. So that's what happens with generations of new systems. Now, we did a couple of really interesting large calculations at the beginning. These were the codes that were used to break into the system. Well, not break into the system, but break the system in to find the problems, to find bad nodes, to fine-tune the software. So a couple of these calculations were really interesting. This is an ocean circulation calculation that was done at very high resolution. Simulations were run on 48,000 cores. We had to work on the software itself to make sure that it ran well. They generated almost a petabyte of data that is still lying around and being analyzed. That was, it's one of those very interesting things that you can do only when you have a full system available to you. So we call those friendly users. The other calculation was, as shown here, is about convection inside a star. As a star of about 25 solar masses. And these calculations were never possible in Canada before. Just a few months ago, actually the beginning of this year, end of 2019, or beginning of this fateful year, we were granted a little bit more money to expand the system. We added another 468 nodes. We had already expanded it a little bit. So we have now a total of just over 80,000 cores. The new nodes are now Cascade Lake instead of the previous generation. And the interesting part from the point of view of the expansion is that the topology of the InfiniBand allowed us to do the expansion in a very seamless and an easy manner. So, I'll tell you about the Dragonfly in a moment. We also added 2 more units of the file system, so now we have about 16 petabytes of spinning disk. The bandwidth is roughly 150 gigabytes a second, so it's fairly reasonable. And it also happens to be fairly well balanced with the size of the system. In addition, we added a few is not very many, 54 nodes of Power 9 with GPUs. These are the same nodes or very similar nodes to what is installed at Lawrence Livermore in Sierra. We added more tape. Our tape here is an HPSS system. And as of this June, we were number 70. We're still tops in Canada, but as you can see, we're sliding fairly quickly down the scale there. Now, what's the story with Dragonfly? Dragonfly has been used for many years by Cray in their networks. This is, again, it's for economics and for balance. You don't have to fully interconnect everybody or every node in order to get sufficient bandwidth and sufficiently low latency. It's just how you balance it. The catch is that you have to do adaptive routing. Mellanox came out with this a few years ago, and it was proposed to us when we went out to RFP. Lenovo proposed this configuration as a way to both making it more economic to do a fully connected InfiniBand at EDR speeds, and also as a way to fairly seamlessly expand the size of the system without having to buy new director switches or to reconfigure the whole topology of the interconnect. So as far as performance, it provides very high bandwidth. Within each of the Dragonfly wings, it's 1-to-1 connectivity. Across wings, it's roughly 2-to-1. But because of the type of connectivity and using adaptive routing, it's effectively as if it were completely fully interconnected. And it, as I say, it uses adaptive routing and congestion control, and that's key in the performance. I put the last line down there, sort of catchy. Should we be running GPCnet and compare? Maybe. It's Gilad Scheiner doesn't think that it's very useful, but it may be a useful thing just to show that the people at HP, by the way, don't know that there is an alternative Dragonfly network that people can use. Originally, we had 4 groups, and the connections allow 432 nodes of one-to-one connectivity. So it's all built up with top-of-rack type switches. So the 1U 36-port switches that are very common. And then those top-of-rack switches are connected to the core. And I will show you the topology is shown here. So the green things, which you can obviously not read, the green things are the nodes at the rack level, the switches, at the rack level. And there are 24 leaf nodes in each one of these groups. The little white squares are the nodes that at the core of the Dragonfly, and there are 18 such cores for each group, such core switches for each group. So to make a long story short, this is very highly interconnected. The topology is kind of weird, but it works really well. Now, when we added a 5th wing, because it was a new generation of InfiniBand, we made it HDR. And even that works. So again, we had a bit of a worry at the beginning. Mellanox assured us that it would work just fine. And in fact, it does. So we have now big capability there because you can do larger number of ports in this group. So it's 1,120 ports at HDR speed. Our nodes are actually connected at 100 gigabits, so it's HDR 100. So you can do almost 3,000 new ports just by adding one more wing. This is, I don't know that there's a whole lot to say. It's just showing you how these things are interconnected. If you have questions about it, feel free. Not that I'm not the designer of this, but I can at least tell you some more. So the difference between this and this is that each of the EDR switches have 36 ports, whereas the HDR switches have 40 ports. Therefore, just that by itself increases the number of available ports. And of course, each of these ports has twice the bandwidth. The limitation to 18 switches in the middle is because of the original design of the Dragonfly. So here's just there's a few more things that are important. The Dragonfly itself, the core of the Dragonfly, consists of 3 racks that look like this. This was just the internal wiring that interconnects the leaves, the wings of the Dragonfly. It's done using copper because the distances are very short. And there are 18 such groups. There's 4 switches in each of these groups. Each one of the switches corresponds to one of the wings. The reason that it's physically positioned like this is, again, so that we can make use of copper cables, which are shorter and less expensive, as much as we can. Now, this is when we had only the 4 groups. Now, after you connect all the nodes into it, this is what it looks like. So it may look like a whole pile of spaghetti. It's kind of complex, but the technicians that did the installation had it all very well designed in advance. You can see that there is an extra I don't know if you can see my pointer now, this extra level of switches here, those are the HDR switches. These are the EDR. The EDR is pretty much full, but the HDR has lots of space. And there's still room for one more wing in this core. The core it consists of 3 racks with 18 groups of switches. And matter of fact, the thing just works. Now, here's the thing. Okay, so we have the fastest system in the country. We spent all our money. We tried to build a system that's well balanced, that can run all kinds of nice codes. How do we make sure that it actually is used, right? There's lots of stumbling blocks. We have users that get frustrated because they don't know how to use it. There are resources that get misused. People run single core jobs on whole nodes. We're using Slurm, and we allocate by node. So the smallest unit that a user can get for a job is a 40-core node with almost 200 gig of RAM. We have to keep on top of users. We have to make sure that the system is properly utilized. Then, of course, the file systems too. Right? You can have the best file system in the world, and just a few bad codes can destroy it. So what we pride ourselves on, what we think is really the most important thing we do, I mean, a machine's a machine, right? And we can all have a machine that's properly designed, and we can run it well from the technology point of view. But the catch is that we want to do science, and so this is our, I wouldn't even say arguably, we are convinced that the most important thing we do is our training and education. We in Canada do not have big centers like the big centers in the UK or in Germany or in the US, or centers that, in addition to running the large systems at tier 0s and tier 1s, they also have research capability. They have hundreds and hundreds of staff. We don't have that luxury. What we have is a few centers in Canada with relatively small staff. All told, we're 16 or 17 people running this, and we have to both run the systems and do all the user support for them. So what we ended up doing is a lot of training, a lot of courses for our users. And that's what we pride ourselves in. So we have a very large training program. And, as I mentioned here, when you get questions from users about science, as opposed to about, how I turn on the machine or why is it crashing, then, we're all benefiting. We get very happy when we're talking science with all our users. After all, we're all scientists in our formation, and we want science to be done. I will end just with a couple quotes from some users. Well, you can read them. And I want to thank you for your attention, and I welcome any questions. I would love to establish contacts, collaborations with anybody who might be interested. And thank you so much.
Thank you, Dr. Gruner, for that great presentation. I currently don't have questions in the queue, but I'd like to open it up to any of our panelists and speakers if they have any questions for you.
Hey Daniel, a quick one. Do you know what is the utilization, how much the system is being utilized today after the extension?
You can add as much as you want and it still gets fully utilized. It's roughly about 95%. This includes some downtime that you have to take maintenance downtime, and also why it doesn't go to 100% is because of scheduling inefficiencies. So especially when you're trying to schedule large jobs, you have to make room for them. We fortunately have a large enough system that we can mix and match all kinds of sizes of jobs. So they range from single node to I don't know, 1,000 node jobs on a regular basis. So it's basically about 95% utilization.
Yeah, thank you for that. By the way, one more comment. You mentioned that Niagara was the first Dragonfly Pass system in the world, which is completely true. After Niagara, I think that there are many more followers of other systems that are utilizing Dragonfly Plus as a topology. I think you mentioned the advantages, right? On one side, you can get similar performance to Tetra on one side. On the other side, it's a zero cost for expansion, and that's kind of the great advantage. So today, around the world, I'd say there are at least 10 large-scale systems that are built on Dragonfly Plus topology. And we start seeing the first announcement of Euro HPC systems, and we'll probably see more coming, more announcements. And the ones that were announced also moving and using the Dragonfly Plus. So I think from my side, you should have a big sign. We were the first, and we show the world how we can build a more innovative infrastructures for supercomputing.
Well, listen, we placed our trust in you. Maybe it was foolish, maybe not. It turns out it was a good thing. We're not shy about going with cutting edge. We did it with Accelero as well. We were one of the first Accelero installations, which actually works very well as well, also, on top of InfiniBand. Can you share who else is doing Dragonfly? I'm just curious.
Yeah, no, there are some that are open. There are some that are confidential. So I'm trying to see which one can we say it. ECMWF, they're going to build a large Dragonfly Plus. DWD is Dragonfly Plus. DKRZ now, so that's Dragonfly Plus. NCI in Australia is Dragonfly Plus. NASA is built Dragonfly Plus. There is 1, 2, 3 that cannot be named, and a good portion of Euro HPC systems that will leverage InfiniBand will be Dragonfly Plus. So those if things will announce, you're probably going to see the ones that announced. I think the two that announced, at least one of them is Dragonfly Plus, and I assume that we'll see more.
All right, interesting. Thank you.
Dr. Gruner, I do have one question that just came in, and that is, can you comment on fault tolerance, reliability, and availability of the system?
To be fair, there isn't a whole lot of fault tolerance built in. In fact, there's actually very little. We have a single power supply. Even though we now have a generator, we cannot cover the whole of the system on the generator. We have UPS only for critical systems, and especially the file systems and some critical central services. So no, if a node dies, it dies. We have not built in any of these, really necessary reliability features. So the file systems themselves, of course, they're disks fail. We are using the GPFS with their GNR distributed RAID. It has been very resilient from our perspective. A disk fails on occasion and gets replaced, but nobody's the wiser. Nobody notices really. The The NVMe has been extremely stable. It is served out of, I believe it's 10 servers, each with 8 NVMe devices, or maybe it's 8 servers with 10 NVMe devices. I don't remember. That one has also been very stable, but it's a fact. I mean, nodes do go down. Sometimes it's because of user code that overdo the memory. The nodes. But there's not a whole lot we can do. Power glitches very often take the system down. So yeah, that's one of the most critical issues for exascale, is how do you build a system that has these reliability components in it. I don't know that this has been solved. I mean, there are people checkpoint as a way of mitigating to some extent, but it's still not the same as being able to recover from a failure on the fly. I don't know that actually works anywhere.
Thank you. I think that's our last question too. So thank you again for the great presentation.